Okay, thanks for coming to the last track, and we'll have two professors to present their latest work. So the first one is from the National University, Professor Guo, and today he's gonna present the topic about the consensus algorithm, which will build on his. So let's welcome him to his presentation.
All right, thank you for the introduction. So I've noticed that you guys just mark this talk as an advanced talk. So when I say a talk is advanced, I'll assume that this will be boring, contains lots of proofs, mathematics, equations, weird notations. But the good news is that today in this talk, you won't see any proofs, you won't see any notations. So yeah, hopefully after this talk you'll find this is intuitive and somewhat interesting. Okay, so I'm going to start this talk by explaining the title. Okay, so I believe that most of you have known some consensus algorithms like proof of work or proof of stake. So today, again, the talk is about consensus algorithm, but we're going to consider different setting. Okay, so we all know that proof of work or proof of stake, they are for public blockchain, but in this talk we're going to focus on private blockchain, okay, which will be mentioned in a while. So throughout this talk, you can imagine that we have a blockchain, and in this blockchain we have 4 nodes, and we already have 4 blocks on the blockchain. And the question now is how to produce the 5th block on the blockchain. Okay? And here we only have 4 nodes, it is Chris, Bob, and David, and they all have their own block, candidate block. Now the question is which block should be the 5th block on the blockchain. Okay? And what makes this problem difficult is that we all know that in blockchain we have some 14 nodes. So 14 nodes are just some nodes that may not follow protocols or rules. Okay? So yeah, so today this is our goal to reach consensus. And yeah, because with the presence of 14 nodes, we cannot guarantee that all nodes to have the same blockchain. So instead, we're going to focus just on the good nodes, and we want to make sure that all the good nodes can receive the same block. And as I mentioned earlier, we consider private blockchains. So this just means that basically not everyone can join the system. Okay, only special nodes can join the system. And in private blockchains, we can reach consensus by exchanging messages. Okay, and usually when you design consensus algorithm for private blockchains, you have 2 requirements. The first one is called safety. So in the world of blockchain, this just means that you cannot have fork in a blockchain. And the second requirement is liveness. So this is just that you can guarantee to receive a new block, okay, as long as you wait for a long amount of time. So if a system does not satisfy liveness, for example, this means you may be stuck in some state like deadlock that prevents you from receiving blocks. Okay, so next I'm going to divide consensus algorithms into several groups according to how they perform or reach consensus in the normal case. Okay. So the first group, I call them the 4-step algorithms. So these are algorithms that can reach consensus by just exchanging messages 4 times in the normal case. So examples include hot start or Libra. Okay, so they only need to exchange messages 4 times in the normal case to complete the block. Okay. So we also have some 3-step algorithms, and here you see some very famous consensus algorithms like PBFT, Chandramin, and IBFT. Okay. So now we have 4 and 3, so why not 2? So indeed, in the literature we already have some 2-step algorithms, FAB, Zizava, SPFT, Hydrotrain, and our solution also belongs to this group. Okay. So if you can somehow lower the number of steps you need to reach consensus, this usually implies that the latency or the response time is smaller. So this usually implies that your solution has a good performance. So since there are already some two-step consensus algorithms, so next I'm going to compare our solution with other two-step consensus algorithms. Okay, so here I'm just going to list some drawbacks or downside of the other consensus algorithms and list some strength and advantage of our solution. So for the first three algorithms, the drawback is that cannot guarantee both safety and liveness. Okay? And for the second one, SPFT, they can guarantee both safety and liveness, but the downside is that when some abnormal condition happens, they need to transform their solution into a three-step algorithm. Okay? So this will increase the response time, so this is not good. So our solution, well, should not be surprised that we can guarantee both safety and liveness, and we never use a three-step algorithm. And another interesting property about our solution is that even if the leader, so a leader is just a node that is responsible for proposing the block, which I'll again discuss in a while. So even if the node that proposed the block is faulty, we still have a chance to reach consensus. Okay, so again, this helps to reduce the latency. Right, so next I'm going to just give you some basic ideas that you're going to see in basically every consensus algorithm for private blockchains. So I think every consensus algorithm needs to address the following two questions. So the first one is, who can propose a block? Okay. So recall that we consider private blockchains. So this means the set of nodes that are in the blockchain is fixed and is known in advance. So usually we're just going to choose one of them from the node, the set of nodes. And in the literature, we usually refer to this node as the leader. So the leader will broadcast the block proposal. Okay. And normally in the future, we're going to change the leader multiple times. Okay. So the more precise question to ask is, at this moment, who is the leader? Who can make the block proposal? Okay. So in the first question, you can imagine a system of 4 nodes, A, B, C, and D. And the question is, who can propose a block? Okay. So in our solution, we thought a very simple mechanism to determine the leader. That is, just use some raw invasion. So in other words, all the nodes take turns to be the leader. Okay, so now we've just solved the first question. So who can be the leader? And let's assume that now A is the leader. Okay. Now the next question is, after I know that A is the leader, how to know whether A is faulty or not? Can I trust the leader? Okay. So we know that some node like A may be faulty, so Alice or A may not follow the protocol, or some node like D may be just be disconnected from the system. So can I trust the leader? So next I'm going to give you an example to show that what may happen if the leader is faulty. Okay, so in this example, you see that Alice is the faulty leader, and what she did is to send different blocks to different users or to different nodes. Okay, so you can see that Alice just sent an orange block to Bob and a green block to David. Okay, so in this slide, I'm going to use different colors to represent different blocks. Okay, so and now Bob and David, they see different block 5. Okay. So the problem is, if the consensus algorithm is not designed well, then it may lead to a fork. Okay, because Bob and David, they see different content in the blockchain. Okay, so that's a fork. So obviously, we want to avoid fork in the blockchain. Okay. So basically, every consensus algorithm needs to address this issue. They need to design, in some sense, a mechanism to determine whether the leader is faulty or not. Okay. And the basic idea is to do peer review. So what do I mean by peer review? So peer review is just the process of nodes exchanging messages with each other. Okay? So the message will contain information about the block that he or she just received. Okay? So based on this information, all the nodes can start to evaluate the leader to determine whether the leader is faulty or not. Okay. So later you see some examples, but first I want to decompose the life cycle of private blockchain into two parts. Okay. So in the first part on the left, you can see that the leader should generate the block and then broadcast the block to all the nodes. Okay, so that concludes the first part. And the second part, we're going to do the peer review. So this is just all the nodes start to exchange messages. Okay, so based on this information, we're going to do peer review. Okay, and after the peer review is done, in some cases, we may need to change the leader. For example, the leader is faulty, so we need to change the leader. Okay. And then you'll see that if you want to change the leader, usually this involves some additional message communication. So next I'm going to give you two examples. So one's good example and another shows what happens when the leader is faulty. Okay, so this is the normal case. So here the leader is a good guy. So he just sent the same block to all the nodes. So you see that all the blocks are orange. Okay? So this is the first part of the life cycle. And in the second part, we're going to start to do peer review. So here, node C, since he just received an orange block, so he'll just tell other nodes that he just received an orange block. Similarly, for node D, again, he just received an orange block. So he'll just tell other nodes that he just received an orange block. And so did B. Okay? So after a while, after this information is exchanged, all nodes will know that every node received the same block. In other words, they have agreement and they can reach consensus so that they can commit this orange block to the blockchain. Now that's the normal case. Let's see what happens in a case where the leader is faulty, and let's see how peer review can solve the issue. Okay, so here the leader is faulty, so he sent different blocks to different nodes. So you see 3 different colors, okay, representing different blocks. So in the process of peer review, node C will tell nodes that he just received a green block, and node D just received an orange one, and node B just received a yellow one. Okay. So after a while, after this information are propagated, that are broadcasted, every node will know that basically everyone received a different block. So there's no agreement. So this means in this life cycle, there's no block community. Okay? So this means we need to move forward to the next life cycle. So we need to change the leader, and the new leader will again propose a block, and we will do the peer review again. Okay, so the basic idea of doing peer review is to make sure that whenever you want to commit a block, you need to first make sure that most of the nodes have the same block. Okay, and after that, you can commit a block. Okay, so far what we've seen are just some standard tricks and ideas that you're going to see in basically every consensus algorithm. So next, I'm going to give you some more details about our design. Right. So first of all, again, I want to stress that in some cases you need multiple life cycles to commit a block or to reach consensus. Okay, and if in the literature we also refer to this life cycle as rounds. Okay, so in other words, we may need multiple rounds to reach consensus. Okay, so to give you more details about our design, okay, in fact. First, I'm going to give you more details about about peer review. So you can think about this question. So when can I commit a block? Okay. So the answer and the magic number here is that when I know that more than 80% of nodes have received the same block, then I can commit a block. Okay. So here the magic number is 80%. Okay. So after the peer review process, if you know that more than 80% of nodes have received the same block, then you can commit the block. So if you just apply this version, of consensus algorithm, then actually in some case it will fail. Okay. So next I'm going to give you a fail scenario, which I refer to as the turtle and rabbit scenario. So judging from the name, you know that there are two nodes, turtle and rabbit. And again, turtle is slow, rabbit is fast. But here, of course, turtle is slow in terms of the transmission speed or the networking speed. And the rabbit is fast. Okay? And let's further assume that the turtle and rabbit, they both have 3 blocks, and 3 blocks only on their blockchain. And what they want to do now is to produce the 4th block on the blockchain. And let's see what happens. So in the first life cycle, because turtle is slow, so basically he cannot receive any message. Okay, so yeah, so since he cannot receive any message, so he cannot commit the block. However, for the rabbit, because the rabbit is fast, so he can receive enough messages, so he can commit the block. And let's say the commit block is B. Okay. So for rabbit, the 4th block is B, but for other nodes, well, they haven't decided what is the 4th block. Okay, so this means for turtle and other nodes, they need to move forward to the next life cycle. Okay, so let's consider what happens in the 2nd round or 2nd life cycle. Recall that we were going to change the leader from by some round-robin fashion, so let's assume that turtle is the leader. And let's assume that since turtle is the leader, so he needs to send a block proposal. And let's assume that turtle broadcasts B prime, which is a block that is different from B. Okay, so B is a block committed by the rabbit as the 4th block. And let's further assume that in this life cycle, the network condition is fabulous. So basically, everyone can receive enough messages to commit a block. So all nodes, including the turtle, they can commit this block B prime because the network condition is good and they can receive enough messages. So in short, we have a fork. Why? Because for the rabbit, the 4th block is B, but for the turtle and other nodes, the 4th block is B prime. Okay. So again, we have a fork, and we don't want to have a fork in our design. Okay. So let's try to find the root cause of this issue. Okay. So the reason that we have a fork is because the turtle broadcasts a different block. Okay, so the block proposed by the turtle is B prime, which is different from B, which has already committed by the rabbit as the 4th block. Now, why did the turtle decide to broadcast B prime instead of B? Well, the reason is that it's not because turtle is bad, turtle is a nice guy. The reason that the turtle decides to broadcast B prime is because he is not aware of anything happens in the first round, because the network condition is bad for the turtle in the first round. Okay? So to solve this issue, first of all, yeah, so that's the root cause. So the fork happens because the leader does not know what happened in the past or in the first round in this example. So to solve this issue, our idea is to pass down the knowledge in the past, okay, to the future. Okay? So more precisely, we're going to pass down the results or some partial results of the peer review to the future leaders. So the future leaders can know what happened in the past. And based on this information, the leader can produce a correct block proposal. Okay, so that, let me show you the final algorithm. So if you are the leader and if you want to propose a block, then you need to first make sure that you have collected more than 80% of messages in the previous round. These are the messages for peer review in the previous round. Okay. So after you have collected enough information to generate the block, next, when you want to decide the content of the block, again, you need to determine the content according to the received messages. Okay, so you cannot just make an arbitrary block. Okay, you have to decide the content according to the received messages. Okay, so I think to this point, you may discover that there's a small issue here, because here the rule says that if the leader wants to make a proposal, then the leader must have collected enough information in the previous round. And what happens if the leader just cannot receive enough messages? Well, this simply means that in some round, we may not have any block proposal. Okay. So the question is, in this case, if you cannot receive any block proposal, what should you do in the process of peer review? Okay. Well, an obvious option is to say that you haven't received any block. Then you just tell others that, well, I haven't received any block. That's it. But the question is, recall that the intuition about our solutions to pass down the information that happens in the past to the future. So if in this round you just said that, well, I haven't received any block, then it's like the information propagation just stopped here. Okay? So to further propagate the information from the past to the future, what we do here is to resend the message that is sent in the previous round. Okay? So we're going to send it again in this round. Okay? So this is like we can keep propagating the information in the past to the future. Okay? Okay, so we have done some preliminary tests, and we've implemented our solution on Geth, and we construct a private blockchain consisting of 100 nodes. And these 100 nodes are deployed on 5 different data centers, so each one of them has 20 nodes. And these results are obtained when we set the block size to 500 transactions per second. And notice that just by upgrading the VM spec from T2 small to T2 large, we can almost double the throughput. Okay. And moreover, in this experiment, we haven't adopted any optimization skills like message or signature aggregation or threshold signature. Okay. So in the future, we're going to apply these optimization skills to further improve the performance of our solution. So I think that's it. So thank you.
Any question?
不好意思，我可以用中文提问吗
OK。
那我想问一下，为什么是80%？然后还有就是这个演算法有什么限制或是什么缺点？因为它看起来比人家多很多优点，可是相对应该会有些缺点什么的。
Okay, so the question is about the disadvantage of our solution and why the match number is 80%. Okay. Well, so it has been shown that if you want to guarantee safety and liveness using a two-step algorithm, then you need to assume that more than 80% of the nodes are not faulty. In other words, the number of faulty nodes is less than 20%. That's the assumption that you must have to guarantee safety and liveness. So you can consider this as a weak point of our solution. So we need to assume that the number of faulty nodes is less than 20%. Okay. And what's the other question? Okay. Okay.
So in other words, we can say that under certain conditions that your algorithm can be better suitable. Like we can assume based on the fact that maybe some of the or most of the nodes are honest, they are good nodes. So in that case, your algorithm is better suited in this condition, right?
I mean, compared to what kind of algorithm?
Compared to other kind of algorithms that needs 3 steps or 4 steps or
yes, in the normal case, yes.
Okay, thanks.
不好意思，我也用中文。我问一下，就是刚刚前面因为 Turbo 它比较晚拿到那个，那我的好奇点是，因为 Rabbit 它已经送了第5个 block，right？ 所以理论上 80% 的人他已经看到了 block 5， 所以 Turtle 他在送的时候，他可能也是送一个 Block 5，right？ I mean， 他假如说他是接在 Block 4，
好，我们的目标是要 the fourth block， 所以他们是在做第4个 block。
对，可是因为 Turtle 不知道了嘛，所以 Turtle 他又做了一次。
Turtle 跟 Rabbit 他们都想要做第4个 block。
对，所以 Turtle 其实不知道，可是其他人其实已经收到，因为 80% 的人已经收到了这个 Rabbit 送出来的，所以理论上 Turtle 他送出来的东西，大家应该会 reject 或者是
OK， 所以这边的问题是这样，就是如果 Rabbit 它可以去 commit 这个 block，OK， 那就代表这个 Rabbit 它已经有收到超过80%的。可是这80%的，事实上他有可能他只能送出去，但他收不送达，所以这80%的他可能没有收到任何讯息，所以这80%的他一样，他不知道原来 Rabbit 已经 commit， 所以这个80%是说 Rabbit 就收到超过80%的人送给他的讯息。对，但是你刚刚的问题是为什么这80%他不会去 reject？ 那是因为你可以把它想他的接收的速度也很慢，所以别人传给他的讯息的 latency 也很大。这时候他就没有办法知道说外面的发生什么事。但 Rabbit 他可以把它是网络的中心，所以每一个人送的讯息，他都可以快收到。所以这个时候，其他的80%就没有办法去 reject 那个 Turtle 它的 approach。
Sorry， 那所以感觉有点像是 Node 都有点无条件的接受 leader。
也不一定。那只是说我这边如果是故意想要把这个 form 弄出来，所以我去假设这样的 scenario。去说刚刚这样一开始你3个位置出去。
好，不然我等一下再思考一下，谢谢。
Does the complexity of this algorithm will be fractional since in the phase of peer review, every node need to check all other nodes except for itself?
So yes, as I mentioned in the conclusion, in the future we're going to aggregate this information. Okay, initially in our design, this information are broadcasted by all the nodes. But if you use some mechanism like to aggregate this information by sending this information first to some hub, and then the hub will aggregate this information and then pass to the other nodes. This then will reduce the communication complexity. So, have I answered your question?
Okay, if there is no question, then let's thanks for Professor Guo's presentation.